right, let's get started. As people are filing in, we have been requested by the deans, and by that I mean a whole gaggle, what is the correct collective term for deans? A whole bunch of deans to help with contact tracing by noting down track for where you are in the room and people seated next to you, if you know their names. If you don't know their names, yes. Can't hear me. Better now. Nope. How about now? Yay. Please note down the names of people sitting next to you to help with contact tracing. All right, hopefully everybody had a pleasant and restful fall break. And let us get started. Gathering information, yes. We will give it a minute. All right, let's get started for reals at this point. Topic for today is processes. So in thinking about kind of where we are in the course, we've been talking a lot about high-level programming, programming in the large, and some features of the C programming language. And later on in the semester, we're going to talk a lot about low-level programming, so programming in assembly language and also looking at machine language. And today and next Tuesday, we're going to be sort of looking at that glue layer in between, if you will. We're going to be looking at concepts from operating systems and computer architecture. And we don't really have enough time to give you a proper description of everything that is going on. So we're going to sort of play the greatest hits album. We're going to talk about the process abstraction, how you create processes, exceptions, signals, things like that today. And next week, we're going to talk about virtual memory, the storage hierarchy, caching, locality. So you really aren't responsible for the details of what gets covered today and next Tuesday. But, you know, it's a really fun thing to learn about. This is traditionally, you know, one of the, you know, these are some of the most fun lectures in the entire course, in the sense that, you know, they get your mind twisted in just the right way to really appreciate what modern operating systems do for you. And of course, they'll, you know, hopefully whet your appetite for more advanced courses, such as Foundations of Systems, Operating Systems, and Computer Architecture. All right, so we'll start by talking about the process abstraction. So processes, as distinguished from programs, a process is the execution of a program. A program is just kind of the code. You know, it's what the compiler spits out. It, you know, it's sitting there on disk just sort of looking at you, not doing anything. Once it gets loaded up into memory, once the memory, you know, everything gets set up for, you know, storing local variables, storing, you know, dynamic memory, stuff like that, the operating system gets told where the program is in memory, that passes that information onto the CPU, and the CPU, it's like, go. And now the program is executing. It has a dynamic component to it. We call that a process. So each process is running one program. So a given process might be running, say, Emacs. But there may be multiple processes running Emacs. You might be running multiple of them. And of course, everybody else logged into the same machine can also be running different processes that are all executing the same program. But these are separate executions of that program. They have their own state. They have their own variables. And so a process is what kind of distinguishes between the multiple executing programs, even if they're executing the same code. Now, a process abstraction provides not just it's not just about the housekeeping of keeping track of what's different between this execution of Emacs and that execution of Emacs. Associated with the process abstraction are two key illusions that the operating system provides to the running process. One is the processes believe that they own all of memory. And they don't have to worry about, is there not really, that much memory? Do I not own all of that memory? Are there other processes executing? And believe it or not, this is a really, really good thing for you, the programmer. Because you, the programmer, can write a program not worrying about, are other processes sharing the same memory? Is there not enough memory to go around? You can just sit there writing your program, calling malloc. Now, at some point, you really do run out of memory, and malloc just tells you no. But right up until that point, you don't have to worry about, is there, somebody else's program grabbing as much memory as it can, and how do you share all of that memory? Similarly, processes have the illusion that they own all of the CPU. So a given CPU might be running tens, hundreds, thousands of processes at the same time. And behind your back, the operating system is kind of switching between which process is actually running on a given CPU. And again, for you, the programmer, this is excellent because you don't have to worry about, is there another process running at the same time? Are there multiple CPUs? And you have to worry about which process is running on which CPU when. All of that happens behind your back. You as a programmer don't worry about it. So it's these two key illusions that make your life as a programmer much, much, much simpler. And that's why we really think of these illusions as a really, profound and very fundamental abstraction in how we use computer systems these days. There's a question down here? How do two processes share the same stack? They don't share the same stack. They each think they have a private stack. They may even think it's in the same place in memory, but it's not. And that's the virtual memory abstraction, which we'll talk about. Yeah. So this is what processes believe. ARM is a 64-bit machine, which means that they believe that there's a chunk of memory ranging from address 0 to address 2 to the 64 minus 1, which is a large number. And they believe they own all of that memory. They can just scribble, wherever they want. And each process believes that. But in reality, they don't have access to all of that memory. The memory gets redirected and shared so that all processes are sharing the same actual memory in the machine. And the way this is done is not at a byte at a time, but what's called a page at a time. So on ARMLab, pages are 64K. So there's a chunk of 64K of memory, which effectively has a pointer associated with it. So that when you access a particular page in your memory space, the machine, the computer, follows that pointer to figure out where in physical memory it should actually be accessing. And this is really nice because different processes can all kind of access different pages in physical memory, even if they think they're accessing pages at the same address. The operating system figures out how to share the physical memory of the machine. And in fact, the operating system can do a lot more. It can say, well, if this process hasn't accessed a piece of memory for the last hour, I can actually save that memory out to disk and free up more actual memory for some other process to use. So the operating system does a lot of very clever things to make sharing the memory very, very efficient. And we're actually going to go into a little bit more about how this happens next week. But for today, we're going to talk mostly about the other illusion, which is control flow. So conceptually, all processes think that they own all of the CPU, and they can just, execute and execute code until, as long as they want. In reality, there's a limited number of CPUs in the computer. It might be one CPU, in which case different processes all have to kind of multiplex using that same CPU. Or it could be, 96 CPUs. But if you have, let's say more than 96 students in a class like COS 217, and they're all trying to use the same 96 CPUs, well, again, there is some notion of time slicing or sharing that has to go on. So in reality, for every CPU, it can be executing different processes at different points in time. So processes are time sliced. In other words, this process gets a little sliver of time during which it gets the CPU, it can run, it can execute its code. And a little bit later, the operating system says, okay, you've had enough. You other process, you get the CPU for a little bit. And by switching back and forth between process at a fairly high rate of speed, we're talking about tens to hundreds of times per second, you produce the illusion that every process has CPU available to it. So more specifically, at any given point, a process can be in one of three states. It can be actually running, that is, executing instructions on the CPU. It can be ready to run, but the operating system said it's not your turn yet. Or it can actually be waiting on something. It can be blocked from running. Maybe it's waiting for some stuff to be read from disk. Maybe it's waiting for some stuff to come in over the network. And in that state, the operating system says, well, you're not going to make any forward progress if I gave you the CPU, so I'm going to give the CPU to somebody else. And so you can imagine all of these transitions between these three major states. You can be ready. The operating system decides, okay, I'm ready to give you a CPU, so the process transitions to running. Then either the process has been executing for a while, its time slice that it's allocated has expired, and the operating system deschedules it. It puts it back in the ready state, or the process might make a request. It might try to read something from disk. And reading from disk is a slow operation. It takes milliseconds as opposed to nanoseconds, so that's really, really slow. Yes, that's, milliseconds is slow. And so at this point, the process gets blocked, some other process gets the CPU and can run, and when that byte really does come in from disk, the operating system puts it back onto the queue of things that are ready to go. So over time, any given process might transition between all three of these states: running, ready, and blocked. Okay. So how does all of this happen? Well, each process has a context. So by context, we mean the state of the process that keeps track of where it is during its execution. Now, this consists of a small amount of information corresponding to what's in the registers of the CPU. Registers are kind of these, internal CPU state, just, small amount of scratch memory. We'll go into them very extensively when we talk about assembly language programming. So registers are part of a process's state, but the other part, at least conceptually, is all the contents of memory. And so if you imagine switching between one process and another, what you have to do is save and restore the contents of the registers, no big deal, and you have to save and restore the contents of memory, which, at least conceptually, is a big deal. And this is part of the magic of virtual memory that we'll get into next time, of how this can happen relatively efficiently. So when you transition from one process running on a CPU to a different process running on a CPU, that's known as a context switch, because you save the context of one process, you write it down in some dedicated section of memory that's owned by the operating system, and you load up the context of another process, which you've saved before. And now the CPU, when it resumes executing, it's now executing the second process instead of the one that you just saved. Okay, so questions on this? All right, so let us move on to talking about how you actually create and manage processes. So we're going to look at a series of functions provided by the operating system that let you create a new process, end a process, and just in general manage what it's doing. Now, this is a set of functions that are actually specific to Unix and Unix-like systems. So Linux, Mac OS, Android, basically all of the class of Unix-like systems, with the notable exception of Microsoft Windows. Microsoft Windows does not use this set of functions. They can be emulated, but natively, Microsoft Windows has a different philosophy of creating processes, which we're actually not going to go into. We're going to stick with the Unix philosophy, which basically uses, there are a few more than these, but these are the major ones. You already know about exit. This is how you kill a process, or a process exits. And then creating a process is done using a function called fork, as in fork in the road. There's a function called wait, and there's a function called execvp, commonly just called exec. So we talk about fork and exec as the major functions on Unix systems. So why do you want to create a new process? Well, pretty simple. You want to run another program. You're in a shell. You type in the name of a new command. You want to execute a new program. You want to execute Emacs. You want to execute make. Make wants to execute GCC. GCC wants to execute the preprocessor. So you want to execute a brand new program. But there are also some instances where you have a program and it wants to split itself into two different pieces. So a very common example is a web server, where a web server is sitting there, it's listening for requests to come in over the network. And when a request does come in, the web server actually splits itself into two pieces. One piece handles the request, responds by sending a web page, and the other piece sits there listening for more requests. And that's actually one of the more efficient ways, or more common ways, of writing a web server. So how do you create a new process? Well, on Unix systems, like I said, you fork. So the function called fork basically just splits a process into two. One is called the parent, one is called the child. Later on, if you want to execute a new program, the child might overwrite itself with a different program, and that's exec. But meanwhile, we have fork. It duplicates the calling process. The new child process is exactly the same as the parent, with one tiny difference, which is the only way you can tell the parent and child apart in the code. And the difference is what fork returns in the parent versus the child process. So fork is called once, but it returns twice, because by the time it returns, there are now two separate processes executing. And the one difference that I mentioned is the return value. In the parent, the return value of fork is the process ID of the child. In the child, the return value is 0. So you can write code that looks kind of like this. Check the return value of fork. If it's 0, you know you're in the child, else you know you're in the parent. And now these two branches of the if can actually execute different code. So the parent and child process at this point start running concurrently. If there's more than one CPU available, they actually are running at the exact same time on different CPUs. But if there are, fewer CPUs available, they go into the pool for time slicing. One of them gets into the ready state, the other one stays in the running state. Which one is which? I don't know. This is one of the things that you cannot depend on, whether the parent or the child actually executes first once you return from a fork. Okay. So let's go through a simple example that emphasizes this. So very straightforward piece of code. You notice this new header file called uni.std. This is the Unix standard system calls, of which fork is one. So uni.std declares fork. So we print 1, then we fork, and then we print 2. So let's think about what's going to happen. Think in your mind what you expect the output of this to be. Okay, got it? Here's what I think is going to happen. First of all, the parent process is going to print out 1. Then it's going to execute the fork. So now there are two processes running. They both return from the fork. We're not checking the return value from the fork, so we don't know which one is which. And we also don't know which one actually gets scheduled to run first. So let's say that the operating system decides to give the CPU to the child. So the parent has gone off to sleep. It is in the ready state, but not the running state. The child is executing. The child prints 2 and exits. Now there's one fewer process. The operating system scratches its head and says, you can run now. That happens to be the parent process. So it starts running, it prints 2, and exits. So the printout of this code is 1, 2, 2, where the first 2 was printed by the child, and the second one was printed by the parent. But wait, it could have happened a different way. If you've ever seen the movie Clue, it's kind of like that. Here's what could have happened, but it could have been done another way. What could have happened was the parent prints 1, the fork gets executed, the CPU decides to give the OS decides to give the CPU to the parent prints out 2 and exits, then the child gets scheduled, the child prints out 2, it exits. You get the same output, but it was produced differently. The first 2 was printed by the parent, and the second 2 was printed by the child. Do you care? No, because this is a simple example. But there are many more complicated ways that this can show up. So let us try to do this. Here's a more complicated program. think through it, see what you think is going to happen. Right. Still some responses coming in, so we'll give it another 10 seconds. All right, so what do we think is going to happen? Well, I see a fork in here. Clearly, child is going to print out something, parent is going to print out something. But what do they print out and in which order? Well, the answer is going to be E, but let's take a look through the possibilities. So again, there are going to be a couple of different traces that we're going to run through. First of all, we have a variable x. The variable x gets set to 1. Now we fork. And we have a parent and a child executing concurrently. Now the thing to remember is at this point, the parent and the child are separate processes. They can't influence each other. I mean, they can influence each other, but one thing they can't do is change each other's variables at this point. So what happens is, let's again assume the OS gives the CPU to the child. The child code executes the if PID equals 0 branch and decrements x. Now you notice that this didn't affect what happened in the parent. These are separate processes. Conceptually, they have private address spaces at this point. Remember one of our key illusions. So at this point, x gets decremented to 0 in the child, and we print out child:0, and the child exits. Back to the parent, the fork returns the process ID of the child, so we do the else branch of the if. X gets incremented from its original value of 1 to 2, and we print out parent:2, the parent exits. This is our printout. But wait, it could have happened a different way. We could have set x to 1, forked the processes, the OS gives the CPU to the parent parent increments x, prints out parent:2 and exits. The child gets the CPU, the child executes the PID equals 0 branch, decrements x, prints out child:0 and exits, and we get a different output. And this pipeline, this Unix pipeline, actually executes this little program 10,000 times and counts which line gets printed first how many times. And you can see that there's kind of a bias that usually the parent gets the CPU first, but that's not guaranteed. So 56 out of the 10,000 times, the child actually got the CPU first. Can you depend on that? Absolutely not. Okay, so questions on this example? Yeah? That's right, the processes have separate heaps, so even if this had been dynamically allocated memory, it still would have been completely separate. Yeah. Yes? Even if you have an array, even if you have a pointer, even if you have a struct, even if you have a struct full of pointers to arrays to structs full of pointers to arrays, it's all separate. Yeah. All right. So suppose you want a little more determinism in your life. There's a system call for that. It's called wait. Guess what? It waits. What does it wait for? Wait is executed by a parent process. It waits for any of its children to terminate. And when one of the children terminates, it stops waiting, it returns control to the parent, and it returns a little bit of information that is, was produced by the child, such as the error code, the return value from the child. Okay, so what if we include wait in our program? Notice that there's a call to wait right there. This null just says, I don't care what the child was returning, throw it away, I don't need to know. Okay. Right, we have a strong contingent of A's with some B's as well, and a smattering of D's. Think about this. All right, so what is this going to do? Well, all right, the parent forks the child. Again, we need to consider multiple, traces of execution. Let's say the OS gives the CPU to the parent first. The parent skips over the if statement, hits the null, and the child is still alive, so the parent is going to wait. The OS gives the CPU to the child executes the if statement, prints out child, exits, it's done. Execution goes back to the parent, it returns from its wait, it prints out parent and exits, and so the output is child and then parent. But wait, it could have happened a different way. So parent forks the child. The OS gives the CPU to the child first. The child executes the if, prints out the child, exits, it's done. CPU goes back to the parent. It skips over the if. It hits the wait, but there's nothing to wait for because there's a child that executed and exited. So the wait returns immediately. At this point, the parent prints out parent, returns, and it's done. So the printout now is child, then parent, the same as in the first case. So it's a way of adding determinism to the execution of concurrently operating processes. Yes? If you had not exited from the child process, then the wait would indeed wait until the child process does exit. If the child process never exits, the parent will never return from the wait. At some point, hopefully you will, Control-C the child process or something like that, at which point it exits and the parent gets a chance to exit as well. Yeah. And we won't get into orphans and zombies and all kinds of things that happen when child processes exit, but the parent doesn't wait for them. It's a fun little topic. You can read up on it if you want. The keywords are orphans and zombies. Yes? A child process has all of the rights of the parent. It can create more children, absolutely. Yeah. But a parent does not wait on its grandchildren. It waits only on its children. Yes? These are simplified examples. In reality, there are lots of examples where you might want to either execute a different program, which is actually the next topic, exec, And at that point, obviously the parent has a very legitimate reason for forking, doing something there, and then waiting for the child to finish. Yeah. Anyway, that brings us to exec. Basically, it replaces the current process with a brand new program. You tell it the name of the program you want to execute, and you give it the environment, sorry, not the environment, the command line that you want passed. That is the argv array that gets passed to the child process. Okay, so those are the arguments. So let's say you want to execute the command cat readme. The command that you're going to be executing is cat. The argv array, well, argv of 0 is conventionally just the name of the program. Argv of 1 is the first actual argument. The argv array gets terminated with a null. So you pass both the name of the command and the new argv array into execvp. Now, there are all kinds of variants of exec. Some actually set up a new environment, some search the path, and some don't. Lots of different options, but this is kind of the most basic, most widely used, most vanilla one, execvp. So, what happens if execvp succeeds? It actually doesn't return, because a brand new program is running. The program that did the exec is no longer in existence. It's gone. What if execvp fails? Well, it returns an error value, but just the sheer fact that a program is still executing after calling execvp means that execvp must have failed. And so you don't actually need to check, if the return value of execvp was something, something, something. The way you handle errors from execvp is you just, print out, hey, I failed. Right? This is interesting. Fork, if successful, is executed once, returns twice. Exec, if successful, is executed once, returns 0 times. Kind of a fun little thing. By the way, there's a function called system, which is the combination of fork, exec, and wait. So system basically just takes a command that you want to execute. It sets up all of the parameters for execvp. Then it does the fork. The child does the execvp. The parent does the wait. So it's the combination of those 3 system calls that goes into the function called system. And you can imagine that this is how your shell runs. So within a loop, it, waits for you to type something, parses the command line, figures out the program and the command line that it's going to pass, forks itself, the child does an exec, the parent does the wait, lather, rinse, repeat. The loop continues. This is exactly the code that is at the heart of a shell. Questions here? All right. Our third major topic for today is exceptions and signals. So an exception in operating system parlance is an abrupt change in the control flow of a running program, often corresponding to a change in the process state. Basically, the OS, says, hey, something happened. You, program, can't run for a little while because I got to go off and take care of some business. That is an exception. Note that this is not the same thing as exceptions in Java, if you're familiar with those. Those are handled in the language using this try-catch mechanism. Here we're talking about exceptions at the level of an operating system. Now, some are synchronous. They actually happen because the executing program did something, requested I/O, or divided by 0, or accessed memory it doesn't have access to, and supposed to get a seg fault. And some exceptions are asynchronous. That is, the program is running, and through no fault of its own, the operating system needs to take control back away from it. And maybe it's because the user typed something on the keyboard, or a packet came in over the network, or something like that. So the control flow here is the application program is running, and suddenly it finds itself not running anymore because the CPU was taken over by the operating system to handle that exception. And in some cases, when the operating system is done with that, it will hand the CPU back to the running program. So it's kind of similar to a function call in the sense that, there's code that is executing, and now suddenly code somewhere else is executing, and you might come back to where you were executing code before. But it's different because a context switch occurs, so the operating system needs to save some additional data, and you switch into code being run by the operating system, which requires some extra privileges, because the operating system can do more to the computer than your program is allowed to do. So, 4 basic classes of exceptions. One is interrupts. This is the classic, something happened outside of the computer, or at least outside of the CPU, and the operating system needs to get control to take care of that. So, network packet, keyboard, disk I/O completing, or every once in a while there's just like a clock that interrupts the CPU 100 times a second or something like that. A trap is initiated by the program, and it uses the mechanism of an exception to allow the program to request the operating system to do something for it. A fault is the program did something illegal, executed an illegal instruction, divided by 0, dereferencing a null pointer, something like that. And finally, there's an abort, which is kind of very rare, and it's basically the hardware itself. The CPU decided, I'm in trouble. I don't know what just happened. Memory got corrupted. Cosmic ray flipped a bit somewhere. I don't know. I'm serious about that one, by the way. This is something that actually does happen. At any rate, the CPU decides, game over. I'm going to, terminate this process. In some extreme cases, it might decide to reboot the computer. All right, so summary of exception classes. We have interrupts, traps, faults, and aborts. They differ in whether they're synchronous or asynchronous, and they differ in what happens in terms of returning back to the original program. Sometimes the execution is resumed at the next instruction in the program. If there's a fault, seg fault or divide by 0 or something, then sometimes the operating system might decide to retry that instruction. And we'll actually see an example of this next Tuesday when we talk about page faults. And then an abort, what happens is execution does not resume. It's terminated. All right, but now let's talk about the final piece of the puzzle, which is signals and process control. So a signal is the way the operating system indicates to an application program that something happened that it needs the application program to handle. So a good example of this is you type Control-C at your keyboard. That generates an interrupt. The operating system takes control. It decides the user typed Control-C, and that was really meant as a signal from the user to tell the running process something. And what happens is the operating system sends a signal to the running process, and unless the process takes, special care to handle that signal, the default behavior in this case is that the process ends. But the process can, in fact, handle that signal and do something different. So Control-C does not necessarily does not always kill the process because the process gets a chance to handle the signal. Okay, so a signal is a notification to a process of an exception. So the OS sends a signal to a process. The next time the process gets a chance to execute, instead of executing where it did before, it executes a special piece of code called a signal handler. And like I said, the default signal handler for Control-C just exits the process. But you can actually install a signal handler. So this is a piece of code executed by a process that says, whenever I get a signal of this flavor, I want to execute this function. Look at that type. That's one of our favorite little things called a function pointer. So basically, the signal function tells the operating system, when I get a signal, execute this particular handler function. And let me show you an example of how that is used and why that is used. So let's say a program is writing to a temporary file, but it wants to be neat about it. So, it opens this temporary file, it does whatever it wants with it, and at the end of the day, it closes the file and removes it, deletes the file, the temporary file. But now, what happens if the user types Control-C? Well, the program exits, but the temporary file is still there. It is not cleaned up. And so the solution to this is to install a signal handler that's going to clean up that temporary file. And here's how this works. You actually create a function that closes the file and removes it, and you install it as the signal handler for sigint, which is Control-C. And now, as you're executing the program, if the user types Control-C, execution goes to this function, the file is closed, the file is removed, the program exits cleanly. And it's an important kind of pattern for cleaning up after yourself that uses the mechanism of signals. So that's it for today. Next time we will talk about the next assignment, and next Tuesday we're actually going to talk about virtual memory. So see you then.